Welcome to homework.
In this problem, we're going to be looking at the WKB approximation. We're going to be applying it to the infinite square well and the finite square well. We got a number of parts. We're going to have to motivate this step by step. So let's jump into it straight in. So to start, obviously that the total energy is kinetic plus potential. That's not in dispute. We use the definition of kinetic energy in terms of momentum as p squared over 2m plus u. From here, we can solve for momentum with a bit of algebra to be 2m times the difference in energy between total and potential. And this is also equal to h over lambda, relating it to its de Broglie wavelength. So we can, just a bit more algebra, some problem somewhere. Let's see. No, that looks good. Right, okay. H over 2m e minus u. All right, good. Perhaps I miswrote it in the problem statement. All right, so step 2, we analyze this expression and we ask ourselves, as u increases, what happens to lambda? Well, as u increases, it eventually gets up to energy E. It can't exceed E. So if u is increasing, this difference is getting smaller. It's in the denominator, so lambda has to be getting larger. So lambda increases as u decreases. As u increases, yes, they increase together. So when we're at the extreme case, when we're at this very edge, we expect the potential energy to be equal to the total energy. In that case, our difference E minus U is 0. Thus, the denominator is 0. Thus, lambda goes to infinity right at these edges. Okay? So now let's look at the actual WKB approximation. It is stated, and some justifications provided, that inverse lambda, the integral of it, is going to equal these half integers, n over 2. So let's plug in our lambda that we derived in terms of mass and energy differences. We will have our root 2m e minus u over h dx equals n over 2. We can easily move this h out of the integral and over to the other side, and that will give us the expression we desire. Okay, got nh over 2. Good, and that's what we're looking for. Okay, so now that we have a workable expression, let's try to apply this to the infinite square well. So we know that for the infinite square well, u is, our potential is 0 everywhere inside the well, and then it instantaneously jumps up to infinity. So we can set u equal to 0 in the integral, and our bounds are from 0 to L, recall, just from the length of the well. So we have 2me dx, which we can trivially compute to be 2me times L. And on the other side of the integral, on the other side of the expression, we have nh over 2. Thus, we can isolate E, solve this through, and we will have h squared n squared over 8ml squared, which is the exact result So evidently the WKB approximation works for the infinite square well. We get an identical result. That's pretty cool. What if we do this for the finite square well? So for a finite square well, everything's exactly the same. Ux is equal to 0. The bounds are still 0 to L. So we're left with this integral once more equals nh over 2. So we have kind of a problem. At no point can we does the finiteness of the potential at the edges ever come into these integrals. So if we were to do this, we'd have to end up with the same result. We'd have En equals h squared n squared over 8ml squared. So there's something. So the WKB approximation leaves some to be desired when it comes to dealing with instantaneous changes at the boundaries that aren't just simply infinite. It works best for smooth potentials. If you have something like a finite square well or a potential bump, this is not going to be very effective because you simply have nowhere where you can put that information into the expression. So that's the main thing to take away from this WKB approximation introduction. It can be used for smooth potentials. It can be used for a lot of different things, but it can't be used for these sharp boundaries. And that's it.